Previously, we talked about forces on a charge, and we decided if a charge is moving, then it's going to be subject to a force that's given by this expression, QVB sine theta. Now, in this particular case, if my magnetic field is pointing in this direction, and then if my velocity is pointing in this direction, and if they make an angle theta, then the force is QVB sine theta, using the right-hand rule, thumb towards the right, fingers parallel to the magnetic field. Now you see the force is going to be perpendicular to both, so it's going to be out of the pitch. Your fingers are pointing up this way, your thumb is this way, so the force is pointing perpendicular to the page, out of the page. Now the question is, what if we have a lot of moving charges? Now if we have a lot of moving charges, they are going to subject to the forces, and the forces are going to add up. Now consider the question of a lot of moving charges forming a current. Remember what a current is given by. It's I is given by Q over T. So my equation that we see there, if we divide it by T and multiply by T, we can always multiply and divide by anything we want to. So my equation would look more like this. And that Q over T is actually the current that we see here. V times T, speed times a time, that's a distance. In this particular case, that would be the length of the wire. So my equation becomes ILB sine of theta. Direction is the same. So in other words, what we are saying here, if I have a length of wire subject to a current I, and we place that length of wire in a magnetic field B, making an angle theta with the current or with the length of the wire, then that length of wire is going to experience a magnetic force given by ILB sine of theta. Very similar equation to the equation for a unit charge. Now, let's see this in action in terms of a simulation. Now, we have a magnetic field, a horse magnet. North pole is the orange one here on top. The south pole is the green. You see the magnetic field line going down. And we are going to be able to see the current, the magnetic field, and the force. We call it the Lorentz force. So we close the switch to have a current flowing, and you notice what happens. So now here, out of the positive lead, I have the current coming here, and then coming here. Now, as the current is moving down there, we use the right-hand rule, fingers in the direction of the current. Not fingers. Thumb in the direction of the current. Fingers pointing down in the direction of the magnetic field. So you see the force pushing the wire in the direction of this black arrow here, representing the force, representing what we call the Lorentz force. You see, I remove it and I put it back. Now you can try different things. What about if we turn the magnet, if we flip the magnet, then using the right-hand rule again, the current pointing in the same direction, your thumb in the direction of this arrow. Now your fingers should be pointing up. See, the force is going to point towards the middle of the magnet. Now, what if we reverse the direction of the current? If you reverse the direction of the current, you have to reverse this arrow. If you you reverse that arrow, then the force should be in the opposite direction. And that's what you see.